In part 2 of our lesson on number theory, we will focus on prime numbers and their applications. So to start with the definition, a prime number is any natural number whose only divisors are 1 and itself. And for theoretical reasons, we exclude the number 1 from our definition. So what is an example of a prime number? Well, 5 is what we call a prime. So 5 is a natural number, and it's not equal to 1. And the only numbers that divide it are 1 divides 5 divides 5, but nothing else does. A number that is not prime is something like 6. 6 is not prime. And while it is a natural number, 1 divides 6, 6 divides 6, but 2 divides 6 as well. As a matter of fact, so does 3. And the second you have any numbers that are not the number or itself that divide it, we say that this thing is not prime. So maybe just one more example of something that is not prime is something like 25. 25 is also not prime. And the reason is, well, 1 divides it, no problem, and the number itself divides it, but 5 also divides 25. And in fact, that's the only other natural number that divides 25. So for this reason, 25 is not prime. So let's actually list out a few of the first primes. So what are the prime numbers if you want to consider them as a set? Well, we can't use 1, but 2 is prime, so is 3 and 5. Then we have 7. 9 isn't, but 11 and 13 are. And so are 17 and 19. It turns out that the prime numbers go on forever, and here's the first few primes. I'd like to introduce another definition before moving on to this first example, and that definition is something called a prime factorization. If you look at the number 6, we said that 2 and 3 divide it, and it turns out that both 2 and 3 are prime. In fact, you can take the number 6 and write it as 2 times 3. We call this product a prime factorization. This means you took the number and split it apart using prime numbers. You cannot break this apart anymore, and this tells you what values actually divide 6. Can we do the same thing for 25? 25 isn't prime. What is its prime factorization? Well, let's see. 25 is equal to 5 times 5, and 5 is prime, and so we'd call this the prime factorization of 25. We split it apart by using multiplication, and everything over here is a prime number. Now, there's another way that you can write this. Instead of putting 5 times 5, it's more concise to say, well, that's 5 squared. So if possible, if we have a prime that is repeated, I'll use an exponent instead of writing them out in a row. So 6 is 2 times 3, that's its prime factorization. 25 is 5 squared, that is its prime factorization. And what about 5? For 5 is simply equal to, well, 5. It is its own prime factorization. So if the numbers are relatively small, it's pretty easy to come up with the prime factorization for those numbers. What I'd like to do in example 1 is look at numbers that are bigger and determine their prime factorizations. Let's start with this one, 147. In order to find the prime factorization, we have to think of numbers that can divide into 147. Now, we have a bunch of divisibility rules that we can use for guidance. So, for example, I know 2, 5, and 10 don't divide into 147. But if you add the digits, 1 plus 4 is 5, and that plus 7 is 12, this number is divisible by 3. So let me write that down here. It turns out that 3 divides 147, and the reason for this is if you add 1, 4, and 7, that is 12, and 3 divides 12. If 3 divides the sum of the digits, it divides the number itself. So it maybe wasn't obvious what number actually divides this, but 3 is a choice. In fact, if you take 3 and divide it into 147, let's see, 3 goes into 14 4 times because you get 12. When you subtract, you get 27. 3 goes into 27 9 times, and it goes in perfectly. What this means is 3 times 49 is equal to 47. Therefore, we can take this number and split it apart, and I'll write it like this. 47 is equal to 3 times 49. Now here 3 is prime. I can't break it apart any further, but 49 is not. Can we split this thing apart? I know that 49 is 7 times 7, and therefore I'll put, okay, well, this is 7 times 7. So 3 times 7 is the same thing as 49. All of these numbers are prime, and therefore that is its prime factorization. The prime factorization of 147 is 3 times 7 times 7. Here we have two 7s in a row. I can actually condense this and say, well, this is really 7 squared. The final answer for the prime factorization of 147 is 3 times 7 squared. So this thing here. Let's try this process again, but on the number 120. Step 1 is, if this is not prime, can you think of numbers that divide into it? And since it ends in a 0, I know we can divide 10 into it evenly. So 120 is equal to 10, and that's got to be 10 times 12. Now, neither of these numbers are prime. That means we can split them up further into their prime factorizations. 10 is equal to 2 times 5, and both of those are prime, so we have to stop there. But 12, we can split that apart. That is equal to 3 times 4. 3 is prime, but 4 is not. 4 is equal to 2 times 2. We've ended up with numbers that are all prime. We just have to write down how many of those that we have. We have 1, 2, 3 2s. So you could think of 120 as, well, it's 2 times 2 times 2. And then we have a single 3 and a single 5. So that is going to be 3 times 5. So how do we express the prime factorization of 120? It's 2 cubed because there are 3 of them. So this is 2 cubed multiplied by 3 and multiplied by 5. So the answer for the first one was this, and the answer for the second one was this. Okay, there's one more to consider here. What is the prime factorization of the number 23? So you have to find a number that divides into it. Okay, well, if I go through the list, I know the numbers that don't work. 2 will not divide into it because the number ends in 3, which is odd. If I sum the digits, I get 5, and 3 doesn't divide into 5, so I know I can't use 3. That's no good. 4 doesn't go into 23, nor does 5. And since 2 and 3 both don't divide into 23, 6 doesn't work. I know 7 doesn't work. 8 certainly doesn't work. For 9, the sum of the digits, again, is 5, and therefore 9 is not going to work. 10 doesn't work. And since 3 and 4 don't divide into 23, I know 12 doesn't work. So, these don't work. And at this point, we're basically more than halfway to this number. What does this mean? We're not going to be able to find any numbers that divide into 23 other than 1 in itself. And therefore, that means that 23 is actually prime, and so it is equal to its own prime factorization. In general, the process of finding a prime factorization can be quite lengthy. It just comes down to, can you find numbers that divide into it? If you can, split the number apart. But if you can't, then that number must be prime. One last thing I'd like to mention about prime factorizations is they are unique. So once you find a prime factorization, like for example, 147 was 3 times 7 squared, that's it. There can be no other combination of prime numbers that multiply back to 147. That is it. And this takes me to the reason why 1 is excluded as a prime number for theoretical reasons. Let's say you allowed 1 to be a prime number. So let's look at 147. We said this is equal to 3 times 7 squared, and you're only allowed to use prime numbers here. Well, if you allowed 1 as a prime number, you could also write that 147 is equal to 1 times 3 times 7 squared. Or you could say 147 is equal to 1 to the 5th times 3 times 7 squared. If you allow 1 as a prime number, you can no longer say that the prime factorization of some number is unique. Notice that these two are different. This is a very minor detail, but it is the reason why we exclude 1 as a prime number. And the reason is, when we find a prime factorization, we want to be able to say the one we found is the only one, in that it is unique. In example 2, let's find the greatest common divisor of 6 and 8. So going up to this definition, the greatest common divisor, known as the GCD, of two natural numbers is the largest natural number that divides both original numbers. There is a lot to that definition, so let's bring some meaning to it by looking at this example here. Let's start by listing out the numbers that divide 6, or the divisors of 6. The numbers that divide 6 are 1, 2, 3, and 6, and there is nothing else. Likewise, for 8, the divisors of 8 are 1, 2, 4, and 8. When we say a greatest common divisor, common means it's going to be a number that is on both of these lists. And the greatest means, well, it's going to be the largest of the ones that are common. So on these two lists, these are all divisors, these for 6 and these for 8. Notice that 1, no surprise, 1 is a common divisor. But at the same time, 2 is a common divisor as well. And nothing else is common after that. So when we say the greatest common divisor of 6 and 8, we are referring to the number 2. This number is the largest common divisor between these two lists. And that's it. You can ask this question for any two numbers, 6 and 8, or even something like 84 and 56. The point being, the larger the numbers are, often the more difficult it is to figure out what this greatest common divisor is. Before moving on to finding the greatest common divisors of these two numbers, let's take a second approach using prime numbers to find the greatest common divisor of 6 and 8. Here's how this works. So we're going to do this problem, but in a second way. We're going to find the prime factorizations of both 6 and 8. So I'll start with 6. The prime factorization of 6 is 2 times 3, and that's it. For 8, I believe it was 2 cubed, but maybe just to do some work for this one. 8 is 2 times 4, 4 is 2 times 2, therefore 2 times 2 times 2 is equal to 8, and so 2 cubed, there's 3 of them, is the prime factorization. How can you figure out from this information that the greatest common divisor is 2? To construct the greatest common divisor, you can ask yourself this question. You want to choose numbers that divide both 6 and 8. So, well, 2 divides 6 and 2 divides 8, so they're common. 3 divides 6, but 3 does not divide 8. Anything that you put over here should be common to both of these lists. And you can only use 2, you can't use 3. So I'll put 2 over here. Once you've decided which prime numbers can be used because they're common to both lists, you then have to decide, well, what is the largest exponent that I can put on this prime number? So here, a single 2 can divide into 6, and here, up to 3 of them can divide into 8. If you want to choose the amount that is going to work for both numbers, you have to go with the smaller exponent, which in this case is 1. So for this reason, I put 2 over here because that was the prime that was common to both of these lists. And I can only use up to 2 to the first power because 2 to the first divides into 6. 2 to the first divides into 8, but 2 to the power 3 does not divide into 6. And here we get our answer of 2 to the first, or simply 2. I'd like to try this process to find the greatest common divisor of 84 and 56. So I'm not actually going to list out all the divisors and then choose the biggest one. Instead, I'm going to find the prime factorizations of both and then construct the greatest common divisor after that. Let's start with 84. So first, what is the prime factorization of 84? Well, I know 4 divides into 84. and 21 is left over if you divide 4 into 84. 4 can be split up into 2 times 2, and 21 can be split up into 3 times 7. These are all prime numbers. Here you have two 2's, a single 3, and a single 7. And for this reason, the prime factorization of 84 is 2 squared because you have 2 of them, and then 3 times 7. And that's it. Now, what about the prime factorization of 56? I think I'll put that next. If you look at 56, okay, this is 8 times 7. 7's prime, but 8 is not. 8, well, I know the answer is 2 cubed, but just be careful. It's 2 times 4. 4 is 2 times 2. Therefore, for 56, we have 2, but we have it 3 times, so I'll put 2 cubed. And we're going to multiply that by 7. And here is the prime factorization of 56. I now want to take this information and construct the greatest common divisor of 84 and 56. Like, what does that equal to? Well, any prime that you put over here has to be on both lists. So here I see a 3, but I don't see a 3 down here. We're not actually using the number 3 as a prime. Therefore, I do not want to put 3 as something that can divide both numbers. 3 can only divide 84. The primes that are common are 2 and 7. So I have to include both of those. So I have 2, and then I have 7. I just want to make sure that the exponents I choose are going to be the smallest of the numbers available. So here, you can only use 2 squared, and you can't use 2 cubed. Therefore, the exponent over here is going to be squared. The reason is we're looking for a number that divides both of these. 2 squared will divide 84, but 2 cubed will not divide 84, so I can only use 2 of them. Here's 7 on both prime factorizations is to the first power, so we'll just take the biggest one, which is the same for both. It's 7 to the first. I'm going to simplify this down to a single number. 2 squared is 4, and 4 times 7 is 28. 28 is the greatest common divisor of 84 and 56. In example 3, I'd like to find the least common multiple of 10 and 12. So first, a definition. The least common multiple, or LCM, of two natural numbers is the smallest number that is divisible by both of the original numbers. Again, a very wordy definition with a similar feel to that for greatest common divisor. Let's bring some meaning to it by looking at 10 and 12. Let's start with 10. What I'll do for 10 is, since we're talking about multiples, let's actually list out the multiples of 10. So if you start with 10, the multiples will be 20, 30, 40, 50, 60, 70, and so on. So those are all of the multiples of 10 forever. We can do the same thing for 12. For 12, it's 24, 36, 48, then 60, then 72, and so on. So here we go. We have the multiples of 10 and the multiples of 12. We're again looking for common multiples, and specifically the least of all of them. If you look at this list, here, 60 appears in this spot and in this spot. That means 60 is a common multiple of both 10 and 12. Is it the smallest one? If you look to the left here and here, there are no other numbers that are common. And for this reason, the least common multiple of 10 and 12 is 60. Just like last time, if the numbers get larger, this is really not the best approach to take in finding the least common multiple. But there is a way to figure it out by using prime factorizations. What I'll do is I'll do this problem again, but not with a list of multiples, instead by finding the prime factorizations of both 10 and 12. So let's check that out. If we start with 10, its prime factorization is 2 times 5. And if we do the same thing for 12, I guess 12 is a little more complicated. It's 3 times 4, and 4 is 2 times 2. Therefore, 12 is 2 squared times 3. So here's the prime factorization for 10, and here's the prime factorization for 12. How can you use this information to figure out the least common multiple, which we know is 60? If you want to be a multiple of 10, you have to have both a 2 and a 5 as a factor. And if you want to be a multiple of 12, you have to have a 2 and a 3 as a factor. You have to have those. So this time, when you construct a least common multiple, you have to use not just the stuff that's common, but every single prime that appears. So if you want to multiply to 10, you have to have a 2. So you have to include a 2. This time, we want to include 3 and 5. The reason is, if there isn't a 3 over here, there is no way you can actually multiply to get to 12. So this time, it's different. You actually have to use the 3. And likewise, you also have to use the 5. The question becomes, okay, you now have to use every single prime that appears, but what exponent is going to be necessary to get to the least common multiple? This time, you want to use the largest exponent that appears. The reason for this is, if you only used 2 to the first, there is no way you're going to multiply to 12 because here you won't have a 4. So for this reason, you don't want 2 to the first, you'll choose the larger one and you'll put 2 squared. Now both 3 and 5 only appear once and their exponents are both 1, so we can write it down, but you're forced just using 3 to the first and 5 to the first. If you multiply this out, 2 squared is 4. 3 times 5 is 15, and 4 times 15 is in fact 60. So the good news is that this process here produces the same answer. With that in mind, let's use this process to figure out what the least common multiple of 144 and 300 is. So step 1 is going to be find the prime factorizations of these numbers. I'll put that over here. Starting with 144, let's see, what number divides that? Well, 2 divides it. Oh, actually, if you look at the last 2 digits, 4 certainly divides 44. And therefore, I know we can take 4 out of 144. I think I'll do this on a calculator. If I divide 4 into 144, I get 36. Now, 4 is 2 times 2, and 36 is 6 times 6. 6 isn't prime. We can split that up. That is 2 times 3, and this 6 is also 2 times 3. Therefore, 144 is 2 times 2 times 2 times 2. That's 4 2's. So we have 2 to the power of 4. And the only other prime that we have is a 3 and a 3, and there's 2 of them, so that is 3 squared. This is the prime factorization of 144. Let's do the same thing for 300. Okay, for 300, let's see, that's 3 times 100. 100 is 4 times 25. 4 is 2 times 2, and 25 is 5 times 5. These are all prime numbers. Here we have 2 2's, so I get a 2 squared. I then have this single 3, so I have a times 3. And then I have these 2 5's, and so I have 5 squared. How can I put all this information together to find the least common multiple of 144 and 300? Okay, to be a multiple of 144 and for 300, you have to have a 2, a 3, and also a 5. We want to make sure we're using all of the primes that are available to us. And the only ones are 2, 3, and 5. So I'll put 2, 3, and 5. The rest is, what exponent are we going to put on this? And we want to put an exponent that's going to work for both numbers. Here for 300, we have 2 squared. But here for 144, we have 2 to the 4th. If we want it to work for both, we have to choose the larger of the exponents, which in this case is 2 to the 4th. if you only used 2 squared, it would not work for 144. Okay, what about for 3? Here we have 3 squared and 3 to the first. If we want it to work for both numbers, it's got to be 3 squared, and so I'll put an exponent of 2 on the 3. And then for the 5, well, there are no 5s here, but there is a 5 squared here, and this means you have to use that 5 squared just like this. So here it is. It's not expressed as a single number, but let's actually multiply it out. This is the least common multiple of these two numbers. If we multiply it out, let's see. 2 to the 4th is 16. 3 squared is 9, and 5 squared is 25. Let's see. So I'll do this on a calculator. 16 times 9 times 25 is 3,600. What this means is, if you list out the multiples of 144, and you were to list out the multiples of 300, you would see that 3,600 appears on both lists, and that is the first time that that would happen. In our last example, we'll look at an application of least common multiples. So here in example 4, it says a movie theater runs films nonstop, and there's an action movie that runs for 105 minutes, and a horror film that runs for 90 minutes. And we'll assume there's a 5-minute break at the end of each movie until it starts again. So if we assume both movies start at noon, when will the 2 movies start again at the same time? For simplicity, let's add this assumption that the theater is open for 24 hours, meaning these movies never stop showing. It's a much harder question if we introduced a closing time. So for this reason, let's just make it a little simpler and just assume that the theater never closes. Now, why does this relate to a least common multiple? Let's start with the action movie. So it's 105 minutes long, followed by a 5-minute break at the end until it starts again. So if you're starting at noon and you want to know the next time it starts again, what we'll do is we'll take 110 minutes and add that to noon, meaning that's 105 minutes plus 5 more, which gives us 110. If you want to know when the movie starts again, you'll add another 110 minutes, which is 220 minutes. If you want to know when the movie starts again after that, it'll be 330 minutes. Essentially, you just keep adding multiples of 110 forever. But this is only telling you what's happening with the action movie. What if you also want to consider what's happening with the horror film? The idea is the same. The movie is 90 minutes long with a 5-minute break at the end. So if it starts at noon, the next time it starts again is going to be 95 minutes later. If you want to know when it starts after that, you'd have to add on another 95 minutes, which is 190 minutes. If you want to know when it starts after that, you would again add another 95 minutes and get 285, and so on, and so on, and so on. When the 2 movies start again at the same time is when you get the same number on both of the lists for the first time. And that is exactly what we defined the least common multiple to be. So to solve this problem, what we're looking to do is find the least common multiple of, in this case, 110 and 95. These are larger numbers, so what I'm going to do is use prime factorizations to figure out what this least common multiple actually is. Let's start with 110. Okay, if we want to find the prime factorization of this number, I know we can divide 10 into it, and then we have 11 left over. 11 is prime, but 10 isn't. 10 is 2 times 5. That being said, 110 is 2 times 5 times 11. That is the prime factorization. If we do this for 95, well, I know we can divide 5 into 95, so we get 5 and 19. And actually, both 5 and 19 are prime themselves, so we get 5 and 19. So what is the least common multiple of both 110 and 95? We need to use all of these prime numbers, so that's 2, 5, 11, and 19. So I'll put, we need a 2, a 5, an 11, and a 19. Notice that the most that any of these occurs to the first power, and that means that's exactly the exponent you're going to use on all of these numbers here. So in fact, the least common multiple, as it turns out, is just the product of these numbers, 2 times 5 times 11 times 19. So let's multiply that together and see what we get. 2 times 5 times 11 times 19. That is 20,090. And this is minutes. So the movies start at noon on some given day. And then this many minutes later, the 2 movies will start again at the same time. Now, it might be nice to actually know what that time is and how many days has passed since this happened. I think we need to figure that out too. That is, like, what time is this actually at? Is it AM or PM? And how many days past this day has this occurred? I'm going to convert this number into hours to help me figure this out. So for starters, we know the least common multiple is 2,090 minutes. If you want to convert this into hours, you can divide by 60 because there's 60 minutes for every single hour. So if I divide by 60, I get 34, and I get this 0.83 repeating. So this is some number of hours and then some number of minutes. I would actually like to record this in minutes. Like, what is 0.8333? What I'll do is take that decimal and multiply it by 60. So 0.833 repeating times 60 is about 50 minutes. So here, this is 34.833 hours, but that's really 34 hours and 50 minutes. Where this 50 came from was I took this decimal and I multiplied it by 60. So I just did that right in my calculator. I saw it was very close to 50 minutes, and so I called it 50 minutes. Okay, so if we start at noon and we go 34 hours and 50 minutes later, what time is that? So this is a bit confusing, but let's try to figure it out. So we're basically starting at 12 p.m. on some day. If we add 24 hours to this, we've gone a full day, and it's noon or 2 p.m. on the next day. Now that means you took 24 hours away from 34 hours and 50 minutes. That will leave you with 10 hours and 50 minutes. So you now want to add 10 hours and 50 minutes to noon on the second day. So if you're starting at noon and you go 10 hours later and 50 minutes, that new time is 10:50 p.m. And I would say that's on the second day. On the second day. So there's the solution. Again, we're assuming that the theater is just always open. This film is always running. Maybe not the best assumption. I'm sure we could solve it without this, but that is it for this problem.